Hello everyone, my name is Mehrunisha. I am from group 324 and today's my topic is fundamentals of fluid dynamics. So first we discuss in this the governing equations. The equations governing the flow of real fluids in and around bodies of arbitrary geometry are rather complicated and no general solutions are available. By consideration of the fluid entering and leaving a control volume, we can write down two dimensional equations of fluid dynamics. The first equation appeals to the notion of continuity. The first equation is notion of continuity, and the second equation is expression of Newton's second law. Second is Newton's second law relating the force or stress on the element of the momentum. Momentum flux into and out of the control volume. We often write the vector momentum equation in terms of velocity and pressure gradients in three mutually perpendicular directions. In the general case, there are more variables than unknowns, and further thermodynamic relationships are required to complete the description of the problem. If we assume that the fluid is incompressible so that the density is constant throughout the fluid domain and that fluid is Newtonian, so that the shear strain rate of the fluid is proportional to shear stress. Shear strain is proportional to shear stress. Then the equation are somewhat simplified. The form of the momentum equation based on these assumptions is called the Navier-Stokes equation. That is Navier-Stokes equation. This together with the continuity equation describes the flow of an incompressible fluid. Unfortunately, with these assumptions, the equations are non-linear and cannot be solved for any but the simplest geometries. However, we can often gain a strong insight into the performance of fluid system by making further assumptions to reduce the complexity of equation to the point at which analytically solutions are available. Different assumptions lead to different simplified equations, and if we are those to choose the appropriate equation, we will need to able to recognize the physics of flow. Fluid mechanics is sometimes regarded as something of a black art because it seems that one needs to know the answer before one can solve the problem. So the next is compressible versus incompressible. An important division of flow problems can be made depending on whether the fluid is compressible or incompressible. If a fluid is compressible, then all terms in the equation that relate to variation in time or space of density are zero, and the Navier-Stokes equation are applicable. It is obvious that liquids such as water or oil are very difficult to compress, and most problems we assume that liquids are incompressible. It is equally obvious that gases in biological application will be particularly interested in air are compressible, and the reader is no doubt very familiar with the relationship with the pressure and volume of an ideals. However, for the problems in fluid dynamics, we can show that the compressibility of a gas has relatively little impact on flow phenomena if the velocities are less than about one third of the speed of sound in the fluid. Thank you.